Chem Kids, Campbell here. Our last unit started with the history of atomic theory. And remember when we were going through the timeline, I'm like, oh, I'll talk about those guys later. Well, it's later. So we're going to talk about the rest of the development of atomic theory and where we are currently with our understanding of atomic structure. But before we do that, we're going to start out by talking about light. Because light is actually what explains some of the current model that we have. Now, light, if you think about when you burn stuff, I mean, a lot of times when you burn stuff, you see oranges and yellows. But there are certain things that you burn and you get greens or you can get reds, like fireworks, right? Fireworks have all sorts of different colors. Well, it's been known for a long time that different elements, when they're burned, produce different colors. And now, a lot of times when things burn, the light is just combined into one, and so it looks just to be one color. But if we actually put it through a prism, it will break out into the different specific colors, because each specific color has a different wavelength. Now, let's talk a little more about what light is. Light is actually electromagnetic radiation, which is a form of energy that behaves like a wave. There are three properties of waves that you need to know. The first is wavelength, and wavelength is just a distance, and what it is, it's a distance between peaks, consecutive peaks or consecutive troughs, or really consecutive any 2 points that are the same. You also need to know what frequency is. Frequency is how many peaks pass a given point per unit time. So usually it's how many peaks pass per second, and the unit would then be hertz. So it's kind of a time thing. And then there's speed, right? Speed, we all know what speed is, right? Speed's how fast you're going. Well, it's the same thing for light. It's how fast light travels. But the cool thing about light is it all travels at the same speed. So it doesn't matter what wavelength it is or what color, if it's purple, green, or blue, they all travel at 3 times 10 to the 8th meters per second, the speed of light, which is pretty fast. Now, you need to know how wavelength, frequency, and energy are related. Wavelength is actually inversely related to frequency. So when I have a short wavelength, I have a high frequency. And if I have a long wavelength, I have a low frequency. So we say they're inversely related because if one's big, the other's small. But wavelength is also inversely proportional to energy. So short wavelengths have higher energies, and high wavelengths have lower energies. And what does that mean about frequency and energy then? That means that frequency and energy are thumbs up. They both are related the same way, directly related to each other. So if I have a higher frequency, I get a higher energy. Or if I have a low frequency, I have a lower energy. So wavelength and frequency are inversely related, wavelength and energy are inversely related, but frequency and energy are directly related. Now, this is an electromagnetic spectrum. You've probably seen this before in other science classes. And you can see here's a range of frequencies and a range of wavelengths. So notice how here I have very high frequencies but very short wavelengths. And things that fall in those categories are things like gamma rays and X-rays and ultraviolet rays. These are all the rays that do a lot of damage to your skin. And then, of course, we have our visible spectrum, the things that our eyes can actually see. And then we go down into these longer wavelength, lower frequency side where we have infrared, microwaves, radio waves. Let's talk a little more about this because clearly this is something you need to know. Is that if we look at just the visible spectrum here, right, the violets and the blues, they have very short wavelengths on the order of about 400, 450 nanometers. But when we're down at the red end of the spectrum, we're down around 700 nanometers. So we have longer wavelengths here and shorter wavelengths here. And remember that wavelength and energy are inversely related. So that means that the purple, which has these short wavelengths, have higher energy than the red light here, which has the longer wavelengths. That has lower energy. And the same thing with frequency then, right? Because remember, wavelength and frequency are inversely related. So here, my purples and blues have a higher frequency, shorter wavelength. And down here in the reds and oranges, where I have the longer wavelength, I have the lower frequency. Got it? All right, so I've been talking about how light behaves like a wave, and it does. but it also behaves like a particle. How is that possible? How can something be a particle and a wave? Well, this was a rage. I mean, the debate went on and on and on because you ran one experiment and you could get wave properties, diffraction, interference, but you could run another experiment and you could get particle behavior. In fact, the electromagnetic spectrum itself behaves differently. If we have those longer wavelengths, those radio waves and the microwaves, they behave like waves. Hence, they got waves in the word. And you have these high energy, short wavelength, high frequency gamma rays and X-rays that behave like particles, right? They don't brush your skin like a wave, right? They nail it like a particle. Well, what experiment proved the particle effect? That's actually the photoelectric effect. So you need to know the photoelectric effect demonstrated the particle nature of light. And while Einstein wasn't the one who came up with this experiment, he's the one that was able to use it to explain that light has particle properties. Now, what is the photoelectric effect? What it is if you shine light on a metal, you can eject electrons. Well, how do they know, right? Well, if you eject electrons and you get a stream of electrons, you can do things like light bulbs, right? What's flowing in your house that's lighting your lights are electrons. So they could detect current. But the reason why they decided that this demonstrates the particle nature of light is not all light does this. It's not like you shine the light and eventually the surface maybe gets hot enough that electrons come out. Oh no, you could shine certain light all year and never get electrons to come out, never light those light bulbs. So what Einstein proved was that only certain wavelengths and frequencies would eject electrons. So there had to be a critical amount of energy in order to get electrons to come out of the metal. So for example, with potassium metal, red light, nothing. Nothing, shine it all day long, nothing happens. But if we dial up the energy or the frequency, dial down the wavelength, right, inversely related, then I get electrons to come out. I can light some light bulbs. So the photoelectric effect showed that you needed a specific amount of energy in a particle to get the electrons to come out. It's kind of like throwing rocks, right? They had to have enough energy in order to get those electrons to come out. And that was the work that Einstein did. Now, why do, and we'll see this in lab on Monday, why do certain elements have specific colors? If we look at, well, sodium's kind of boring. That's one of the ones we're going to look at in lab. It's just yellow. But if we separate the spectrum of something like calcium, we're going to see a whole range of blues and some yellows and some oranges and some reds. With mercury, we get some greens, but they're only specific wavelengths. So why is this? Why does this happen? Well, that's actually what led to quantum theory. Planck was like, what the heck? How come only certain wavelengths of light are given off? So if that's the case, right, and wavelength and energy are related to each other, then only specific amounts of energy must be given off when we see these colors. So what Planck suggested is that the energy of an element is restricted to certain amounts, and he called those amounts quantum, or plural, quanta. So a quanta is a specific amount of energy. Here he is actually talking to Niels Bohr, because Niels Bohr used this idea to actually come up with his model of the atom. Now, what Einstein said is that, he was really into the particle nature of light, that light is actually packets of energy. And these packets of energy have a specific amount, and he called those photons. So photons are packets of energy. So light behaves as particles. If we have a lot of them, then they behave like a wave. Light's pretty cool, isn't it? But, okay, great. Light, particles, waves, whatever. How does this explain the spectrum of an element like hydrogen? How can something with a nucleus that has protons and neutrons in it and negative electrons moving around on the outside, how does this explain these colors? So this is where Niels Bohr came in. Niels Bohr proposed a planetary model of the atom. What he said is that we have our nucleus in the center, right? J.J. Thomson said that. And we have these specific energy levels, and only at those specific energy levels can an electron exist. And he numbered those energy levels 1, 2, 3, 4, and on and on and on and on. Now, he said that the lowest energy level, this n equals 1, is called the ground state. And in fact, all particles, even humans, like to be at the lowest possible state, which is the ground state. Now, if an electron absorbs energy, and it has to be a specific amount of energy, it can move up into a higher energy state. So an electron wants to be at the lowest state, n equals 1, but if we hit it with some energy, it can jump up to another level. So it's kind of like climbing stairs, right? It takes energy to go up each ladder of, each rung on a ladder. So energy levels are a specific amount. And as we move away from the nucleus, these energy levels are kind of like stair steps. That energy level increases. In order to move to a higher energy level, then I have to absorb some light. If I absorb some light, right, light has energy, an electron can jump to a higher state, and we call that an excited state. Woohoo, we're excited! But eventually, right, we lose our excitement, and we fall back down to a lower level, like climbing down the ladder. I hate heights, so I won't stay up on a ladder very long. I want to get down. So light is emitted when that electron falls back down to the lower level, but it's a specific amount because that energy difference between those levels is a specific amount. Now, Bohr actually did this, and he actually was able to predict every single spectrum, every specific wavelength in the hydrogen spectrum. Pretty cool. So what does hydrogen look like? And I'll actually have this set up in class, and you can use a spectroscope. And here's a tube containing hydrogen, and hydrogen actually breaks into 4 visible lines. And if we look at what's happening actually with hydrogen, the longer wavelength, which is the low energy one, is actually a drop from energy level 3 to 2. And this blue-green one here is a drop from 4 to 2. And higher energy, right, I fall farther, is a 4 to 2. And I think this 410 is actually a 6, or that's 5 to 2, 6 to 2. Now notice none of them are falling down to the ground state for these. What does that mean? Because I thought you said, right? I said everything likes to be in the ground state, right? The lowest possible energy level. Well, there are lots of jumps, right? Any of these combinations is possible. The problem is we can't see them with our eyes, right? We're limited into the wavelengths that we can visibly see. So this is actually called the Balmer series. But there's also a Lyman series and a Paschen series, and those are ones that have different amounts of energy that when we calculate them in terms of wavelength, they're not visible to our eye. They're there, but we can't see them. All right. I can't wait for lab. See you in class.